Hello, everyone. I'm Lingyun from the State Library of Information Security at the Institute of Information Engineering, Chinese Academy of Sciences in China. It is an honor for me to share my research findings on the topic of a post-quantum privacy-enhancing blockchain-based transaction framework with access control. In the subsequent section, I will address the background, motivation, problem statement, proposed system, results, and discussion, and finally conclude with a summary. Firstly, I will provide an overview of the background. Blockchain technology plays a vital role in enabling decentralized peer-to-peer transactions through distributed storage and computing. On one hand, blockchain technology offers a certain degree of privacy protection for traders by ensuring transaction anonymity. However, on the other hand, compared to traditional centralized transaction, blockchain-based transaction system expose transactions to all nodes in the network to achieve consensus. This exposes transaction information to analysts, potentially compromising the privacy of the traders. To show this issue, let's consider the example of Bitcoin, which employs a typical blockchain mechanism. In Bitcoin, the transaction ID is derived from the hash value of the trader's public key. By tracking the transaction ID in the global ledger, an attacker can access information such as the fund balance, the distinction of funds, or transaction associated with a specific account or a specific coin, and the transaction information and the rules between different transaction IDs. Moreover, by combining network layer attack technologies like IP tracking, as well as social engineering attacks of application layer and etc., attackers can obtain additional private transaction information. Variety privacy preservation technologies have been proposed for blockchain, including restricted address detection and shielding of malicious nodes, anonymous communication network, and cryptographic technologies such as encryption, group signature, or ring signature, etc. However, these technologies only address specific aspects of privacy preservation in blockchain and come with their own limitations. In our research, we combine the privacy preservation issue in blockchain with two key post-quantum crypto systems. These are hash-based signature and lattice-based encryption. Hash-based signature and lattice-based encryption are both considered as crucial post-quantum crypto systems that provide resistance against classical and quantum attacks. They have gained significant attention in current cryptographic research. The first one, hash-based signature, which is used for message authentication and entity identification, is designed by combining one-time signature or few-time signature with public key authentication hash tree, and its security only based on the security assumptions of the underlying hash functions. And most existing hash-based signature schemes achieve EUCMA security. And Typical schemes of hash-based signature include XMSS, LMS, Sphinx Plus, Gravit Sphinx, and etc. On the other hand, lattice-based encryption is considered secure based on certain well-studied computational lattice-based problems. Some typical lattice-based encryption schemes include the GGH encryption scheme based on the closest vector problem, untrue with shortest vector problem in a lattice, and Gentry's fully homomorphic encryption scheme, BGV, fully homomorphic encryption, and so on. These two post-quantum crypto systems form the founding of our research. And next, I will discuss the motivation and the problem state. Let's consider the following model. Suppose there is a sales company with multiple sub-departments organized in a hierarchical structure with hierarchical authorities. The highest level sub-department is directly supervised by the CEO, while the lowest level ones directly manage the traders. Given the high security nature of the transactions on the public blockchain, the company desires the traders to conduct transactions directly through the public blockchain. However, the company still needs to evaluate its employees based on transaction values, amount, and other indicators. To achieve this, traders must submit their transaction information, which can be verified to prove that specific transactions were executed by themselves. Therefore, it is crucial that the submitted data is genuine, effective, and verifiable. And addressing this requirement, our research aims to develop a blockchain transaction framework that allows traders within a hierarchical transaction organization to conduct transactions using the public blockchain and ensures post-quantum security while providing privacy preservation through access control and realize post-quantum security. By utilizing the hash of a key as a transaction address, while by using this one-time public key, the hash of this one-time public key, which is secretly associated with a specific trader, the corresponding one-time private key, is transaction on the blockchain. And this approach effectively prevents unauthorized tracking of transactions. And moreover, we creatively use the hash of one-time signature twice to ensure managers can access and track transactions. Before introducing the system, let me first present the three kinds of participants involved in the post-transaction system. As we have shown before, the first two are managers with authorities at all levels and traders. The authority table of the proposed system is shown here. If A is in any subtree with B as the root. Here, if A is in any subtree with B as the root, A is managed with B's authority. For example, where traders LV36 and trader LV37 are managed within manager LV23's authority. Okay, the third participant is authority center. And here we write it as, we denote it as CA. The authority center is a trusted participant accountable for verifying, recording, and managing transactions information for traders. When manager requests transaction information related to traders within their authority, the authority center verifies the requesting manager and then provide the requested transaction information. Okay, all right. Next, we will discuss the proposed system, which consists of seven sub-algorithms. Okay. The first one is executed by each participant in the system to generate forward secure one-time private keys and public keys for the one-time signature in this hash-based signature scheme. And in this algorithm, each one utilizes the PRF. Here, PRF is the pseudo-random function to generate a seed sequence. And this ensures that the resulting signature scheme achieves forward security. And the second algorithm, which is executed by each one in the system to generate their root public key for the hash-based signature. As we can see here, the participant establish their own root public key authentication hash tree, bimorphic tree here, which comprises all their one-time public keys, into a single root public key, and we call this the root public key of a hash-based signature. And the third algorithm is executed by each one to generate his private key and the public key of lattice-based encryption. To generate the key pairs of lattice-based encryption. The fourth algorithm of PKS. I will introduce this algorithm in detail. It is executed between managers and their managers of one level higher, as well as managers of one level higher and the authority center. The purpose is to authenticate and store the root public key of hash-based signature and the public key of lattice-based encryption. That is two public keys. two public keys for each manager by authority center. Okay, here's a breakdown of the steps involved in this algorithm. Firstly, all the manager except the toppest one sends their identity evidence informations and two public keys to the manager of one layer higher, and we denote them as manager I and manager I minus 1 here. And this communication occurs through a security channel. Secondly, manager I minus 1 check whether the identity proof information provided by manager I matches their identity. If successful, manager I minus 1 finds manager I's identity and the above two public keys by one of its one-time signature keys. Then he encrypts the signature as well as the public key of lattice-based encryption and pass in this to form a complete signature, and then he used the public key of lattice-based encryption of authority center to encrypt the two PKs, the signature, and the ID of manager I, and then send to authority center. The authority center decrypts and verifies the self-test received from all the managers. First, he checked all these following the order of their authority, following the order of their authority from top to the bottom order. And once the top-down authentication is completed, the authority center maintains a public key record table that contains the IDs of all managers and their corresponding two public keys. And the fifth algorithm is the transaction algorithm. Here, trans is a transaction algorithm used by the trader in the public chain of the blockchain to complete transactions. It follows a transaction model similar to Bitcoin, but with the only difference that the signature in the transactions is realized by utilizing hash-based one-time signature. Here, in each input of a transaction, it contains a hash-based one-time signature, and the corresponding one-time private key is just used to sign unique transactions, and this prevents the unauthorized tracking effectively. And the next algorithm, the sixth algorithm, transacts, is executed between the traders and their authority center to authenticate and register the public key address of the traders. This occurs according to a certain time interval or transaction frequency. Here are the steps involved. For each hash-based one-time key pair used in this current time interval, the trader searches for the corresponding one-time public keys in the input of the transaction and search its hash values in the outputs of the transactions within the public chain of the blockchain. The trader then finds the connection of all the hash transaction hashes. Here, TXH denote the transaction hashes of this transaction along with their own identity and current timestamp using the private key of one-time key pair and the resulting signature along with the trader's identity, timestamp, and public key, and the authentication path of this public key is considered the transaction evidence. Considered as a transaction evidence for this particular one-time public key. After generating transaction evidence for all hash-based one-time public key pairs used in this current time interval, the trader connect them together here. Here, the traders connect them together and then encrypts them using the public key of the lattice-based encryption owned by the authority center and send the resulting ciphertext to authority center. The encrypted ciphertext containing the transaction evidence is then sent to authority center. The authority center performs verification and registration here. In this way, the authority center can authenticate and register the public key addresses of traders' transaction within the specific time interval or transaction frequency. In this way, the authority center authenticate and register all the public key addresses of the traders. Okay. The final algorithm, transacts. It is executed between the manager and authority center based on access control and ensure that the manager can access transaction information of the traders within their authority. And this algorithm operates as follows. First, the manager generates transaction access request. Let's see how he generate this request. First, they use their one-time private key to sign the request along with the timestamp and take it as a complete access request to the authority center. If this request needs to be kept confidential, if this request needs to be confidential, the manager can encrypt it using the public key of lattice-based encryption scheme owned by the authority center. On receiving the request, the authority center authenticate the manager and provide a reply. By this way. First, if this request is encrypted, here is a decryption for this self-test. And then the authority center verifies the access authority of this manager in the request. Then verify the one-time signature and the authentication path and the root public key. And finally, he reply to the transaction request with signing and then encrypting the above information and send it back to the manager. When receiving it, the manager decrypts and verifies to the corresponding subtest and obtain the requested information. Okay, that's all for the proposed system. Let's start with the security. The proposed system offers robust security measures, including post-quantum forward secure, EUCMA, and IND-CPA secure in the semi-honest model by meeting the following conditions. These are post-quantum PRF. Here PRF denotes the pseudo-random function. Post-quantum one-way hash functions. The post-quantum EUCMA of the underlying hash-based one-time signature, and post-quantum IND-CPA of the underlying lattice-based encryption. Okay. Now let's discuss the system's efficiency. We conduct evaluations to measure the computation cost and communication traffic of 7 algorithms within this system. Here are the results. To conclude, this paper presents a framework of a transaction system that incorporates access control based on cryptographic tools in a multi-user transaction organizations operating on the public blockchain. And the system utilizes hash-based one-time addresses to safeguard transactions from unauthorized tracking, and introduces a creative use of hash-based one-time signature for both verification and transaction tracking purposes. Compared to the standard Bitcoin transaction system, the proposed system achieves post-quantum security in the semi-honest model. Okay, that's all for my work. Any questions?